is going to discuss AI hardware at the edge and the many interesting challenges and opportunities that it has. So I'd like to start by introducing the panel, but rather than me doing a poor job, I will ask them to just say 1 minute about themselves, their current roles, and their interest in this area.
Thanks, Jesús. My name is Rajesh Pankaj. I work for Qualcomm. I'm a senior vice president of engineering there, and also the head of the corporate engineering, corporate R&D group. And I wanted to tell you why Qualcomm would be interested in AI hardware, but Song did a pretty good job of telling you, how he's running all of those algorithms on Qualcomm chips. So really, if you're using an Android phone, most likely you have an AI hardware engine that's sitting inside your phone that was made by us. My group does advanced research on that. Also, we work on some of the algorithms that Song earlier talked about, and also the software that actually goes out to commercialization. So all of those things are done by us, and of course, we are super interested in all sorts of AI hardware.
Hello, thank you. My name is Joel Emer, and I'm a professor here at MIT. My area of interest is in processor architecture. So I have a long history of working on general purpose processors for mostly improving performance, but more recently, much more of a focus on energy and efficiency, efficient performance. More recently, that's migrated to focus on deep learning and other more specialized computation. At the end of Moore's law, we've had to turn to focusing on specialized engines and how to optimize within a domain instead of completely generally.
Hi, everyone. My name is Song. I'm an assistant professor at MIT and also co-founder of OmniML. I work on efficient deep learning computing, including model compression techniques, how to reduce the size of neural networks, make it simplified, lightweighted, easier to deploy on edge devices. And also recently I'm working also on efficient training, how to make it more scalable, less memory consumption, together with the efficient hardware to support the pruned and sparse model to make them efficient on specialized hardware platforms.
Thank you.
Hi, everybody. My name is Varada Gopalakrishnan. I'm a part of Amazon's device organization. I come from the organization that has shipped products like Kindle, Echo, Fire TV, etc. AI at Edge is an integral part of our device challenge. More recently, I'm interested in improving the compute efficiency for problems such as what Song described in the previous talk in terms of improving computational efficiency for executing AI inferences on our devices. There are many applications that I'm interested in the edge. We'll talk about some of them during this panel.
All right, thank you very much. So I wanted to start by asking each one of our panelists to share with us a compelling use of AI at the edge. And I asked them to do this with one view graph, with one slide. So let me see, let's go with Song, because your slide is up.
Yeah, a practical usage is edge AI for automotive applications, in particular for autonomous driving. That require a lot of computation, since that require multiple sensors, such as LiDAR and also camera. Usually, we also have multiple cameras, like 6 cameras, or even like in this case from Waymo self-driving car, 10 cameras, 5 LiDARs, and 6 radars. So the total computation required is more than 200 trillion flops per second. Right? On the car, this is a limited amount of computation. But how do we efficiently process so much data on these sensors in real time, which is, since this is a safety critical scenario, and also handle those challenging data patterns like sparsity, where point cloud is highly sparse and irregular, require a lot of memory footprint. They are not hardware friendly. And how do we do sensor fusion for these sensors from different modalities, like dense camera data and also sparse point cloud data? That require a lot of co-design between the algorithm, software, and also the hardware. So that I think is an important use case of edge AI.
Joel, next slide.
So the
one back, please.
One back. Yeah, so the application of edge DNN applications that I actually think is very exciting is something that you heard about earlier from Professor Kammerman and the work he did with my close collaborator, Professor Z, and that is autonomous drones. I think that this is a very exciting area because of the different opportunities there are for using it. So for example, in going places which are dangerous for humans, disasters, or either man-made or natural, and you can use one or many drones to analyze it. The computation there is very challenging. Professor Carmen talked about some of the navigation aspects, but there's also the analysis of the scene and to figure out what's going on. Could also be in outer space. We've already seen applications of drones on Mars, and so it's, again, a very interesting and very challenging analysis application. Another application is monitoring individuals. So in cases where you need to monitor somebody's state, for example, the elderly, not me yet, but it's something that it would be very valuable to have because the person is going to be able to move around. You're not going to be able to use stationary cameras, and so you're going to have to deal with both the navigation task of tracking the individual and monitoring what they're doing. This is actually something that is of personal relevance to me. I have a special needs son who's quite mobile, but needs to be monitored all the time because he could get into trouble. He doesn't really know what's dangerous or not. And so having a mobile drone that would track him because of energy considerations, I could imagine it perching somewhere and monitoring him for a while, maybe in platooning with multiple drones so that they would be able to alternate recharging their batteries and monitoring, be able to watch it. Again, a very challenging application of both navigation and analyzing the situation.
Yeah, thank you.
Sure. Just waiting for the slide to come up, but I can start talking. I think many of the speakers in the morning and afternoon talked about the different applications of AI that will enable operations in the devices. I think for me personally, latency-sensitive applications, I mean, I have the example of Amazon Astro, which is the home robot that we've recently announced. Latency-critical applications like mobility, I mean, if it's moving at meters per second, you don't have time for this to go to the cloud and come back. And I think we saw the demo of the drone in the morning. The latency-sensitive applications just don't have the time to go to the cloud and come back, and so the edge processing becomes really critical. Song talked about sensor fusion. We have multiple sensors even in this robot. It's not an autonomous vehicle. It's not driving at that speed, but it is navigating a very complex home environment. It's extremely unstructured. So you have a lot of sensors, and the sensor fusion is better done at the edge than in the cloud. There's another interesting aspect of AI at edge, which is the privacy. Again, many speakers in the morning talked about it. You don't want all the data from our devices to go to cloud. So we're very sensitive to privacy promise that we make for our devices, and this is a part of, this is another reason why we believe that edge AI is important. Those are the reasons why I would consider edge AI as a critical for the future of almost all our devices.
Mm-hmm. Yeah, Rajesh?
All right, so I'm going to expand the definition of edge AI a little bit. I agree with everything that was said, but there is also another thing that I want to add. So if you look at the slide on the right-hand side, there are all these little devices where the AI could be running. But if you have access to low latency communication, and on the other side of this low latency communication, you have some significant, it could be just a little bit more than what you have on the edge device, on the device there, just a little bit more, then you can do quite a bit more. I will give you an example. You may have a little sensor that can do a little bit, but maybe on the other side of the low latency communication channel, you have a smartphone that has a lot more capability. Of course, you can have slightly more capable device at the very end, which is collecting data, and then maybe a bigger computer which is sitting on premises. So I think of edge computing or edge AI in a little bit more expanded fashion. Of course, the final device that everybody talked about, that is included in the kind of edge AI that I think about. One example that I will give you that I actually have had discussions with actual customers who are interested in this. The point that Varada made about privacy is of course important. But in this particular case, this was a big box store. They have security cameras that's actually monitoring these self-checkout counters, and they don't want this data from the self-checkout counter to go to the cloud for various reasons, and latency being one of them. And so what they try to do is that in the same box store, they may have this little device that does the self-checkout, but also in the same box, the same building, they have a more powerful computer that's sitting there. It sends the relevant video clips over there without having to go all the way to the cloud. It's low latency enough that it can find out if there is any particular issue, sends the information to the greeter who is sitting there or the security person who is sitting there, and make sure that it can close the loop very, very quickly. So that's one example that I can give, but of course a lot of other examples that were talked about before are equally relevant.
Great, thanks. So we've now seen very compelling applications of AI at the edge. And so I'd like to focus the next question on the needs for AI hardware to make this possible. What are the needs and what are the challenges to deliver the hardware that will make all these come together? Joel, please.
OK. Yeah, that's a great question. And actually, we've seen a lot of discussion in previous presentations on the need for efficient hardware. Talked about number of computes that's been growing dramatically. We talked about pruning the weights in order to reduce the amount of computation. When I look at it, what I recognize and see is that data movement is actually much more important than the compute. The energy consumed in data movement can be 1 to 2 orders of magnitude more to do a single operation than the compute part. And so a lot of our previous work has been, well, how do we optimize for the data movement? Basically, how do we schedule the data so that we move it minimally in order to save energy? And one of the ways that we've done this is by deciding that certain values should stay still so that they can be reused or they remain stationary for longer periods of time. Mm-hmm. So that has resulted in things like thinking about something as being input stationary or output stationary in order to optimize the behavior with respect to reuse. But that work has almost all been focused on doing one layer of the network at the time. And there's a large amount of intermediate data between the layers that you have to pass between. Now you can think about if you have an output stationary data flow, we call it, and an input stationary data flow, then the amount of data being created is small, and so you can merge those together. But that only works for 2 layers. And so what we've been thinking about and trying to architect is sort of the oxymoronic notion of an input and output stationary data flow, so that at both sides there's minimal amount of data that's being held, and so we don't need to slosh that data out to large storage. Couldn't even put it on chip because having a large storage on chip also has a lot of energy. Mm-hmm. Okay.
Varada, please, AI hardware at the edge.
Yeah, this question, I think Song's previous presentation covered almost all the answer I wanted to give for this question. So I'm going to take it in a slightly different direction. So I think that presentation very ably described the diversity of the hardware that is present in the world today. I mean, from, you mentioned M7, we have M4s that we don't, some of our devices can't even afford an M7. So you have M4, Cortex M4, which is the low end, to high-end Cortex A7, A series, and then you have DSPs, dedicated hardware. We have all of it. The challenge that I see in this is how do we develop a good software abstraction that can effectively use any and all available compute systems on an SoC or a system on chip. that is still a challenge. I mean, we have very good abstractions for a single system, either it's a CPU or a DSP or an efficient ML engine. But how do I use it across all of them and distribute where the load is best suited to run for? And that's one challenge. So that's basically a software abstraction. So I know it's a hardware question, but I felt that it's important to call out the system problem that we deal with. The other question quickly, the other comment quickly is that so far today in the conversation, in all the presentations, we focused heavily on deep learning, neural network, different types of neural networks, convolutional neural networks, transformers, different types of neural networks. But the neural networks are only a part of an end-to-end systems we build. If you take the robot that I showed or the autonomous vehicle that Song showed, there's a bunch of other critical systematic computes that are done, like a SLAM problem that's rich in optimization problem. How do we integrate, how do we develop better hardware that can effectively utilize, that can be effectively utilized for not just deep neural network, but also for other types of linear algebra-rich operations like optimization problems. I think many of Song's and others' talk today covered different types of neural network accelerator. We have our own, one in the cloud, one on the device. We call that AZX for the device and the Inferentia for the cloud. But I'm also interested in expanding it beyond just the neural network. How can we do other linear algebra operations? So I'll pause there.
Yeah, thank you. Rajesh, AI hardware at the edge.
So I will go a little bit beyond what Varada said. So we are used to we have been making chips for mobile phones, which are very, they have to be power efficient because you want the battery to run all day. So we are used to designing these different cores that are specifically designed for different tasks. And we have to do the same thing for energy-efficient AI hardware also. Actually, the AI engine that sits in your smartphone has different little cores that are actually they are best suited for different operations, even for a neural network processing. And of course, the software that needs to be there in order to make sure to take advantage of the right core for the right calculation. It turns out actually that in our different tiers of chips, we don't have the same set of cores. So we develop all of these different cores, but some cores go every core goes in the premium tier chip, but when you go beyond that, go below that, not every core will be available. And of course, our software has to be well designed to make sure that it knows what cores are available and then maps the computation that it needs to do for neural network onto the right cores, which I think is going to be key to do power-efficient AI processing on the edge.
Mm-hmm. Thank you. So, what can you add to your wonderful presentation?
Yeah, hardware. Yeah, since I feel there's plenty of opportunity, both on the top, on the algorithm side, and also on the hardware side, where given there's huge opportunity to simplify and reduce the size, the computation, the activation of neural networks, hardware design should be supportive for that. Like the sparsity generated by pruning is not friendly on those dense computing hardware platforms. So how do we support sparsity, especially at different granularities? There's coarse-grained sparsity, fine-grained sparsity, and also structured sparsity and unstructured sparsity. And how do we take advantage of the whole design space to co-design the hardware with the neural network is very interesting. And since the total size is a multiplication of the number of weights with the number of bits per weight, so reducing the weight, bit precision is also interesting to explore by using quantization, weight sharing, or pelletization, or even a low precision floating point, right? And it's getting very interesting where we are going from 32-bit to 16-bit, B float 16, or even 8-bit floating point, where we can we share some of the exponent among a block of numbers to reduce the total number of bits. So those are all interesting factors we can consider for future silicon design for edge AI. And in the meantime, how do we fit neural network on the hardware is also important. For example, if we try to fit a square into a rectangle, they won't fit. right? So hardware-aware neural architecture search can potentially bridge this gap to design the best fit neural nets with the best hardware accelerators. And another question is how can we design them together, opening the design space to co-design, to co-search the neural network architecture, the compiling, the mapping, and also the accelerators architecture together and have a push-the-button solution. Given different constraints, just generate the neural network, generate the hardware automatically to improve the productivity of such hardware design would be also very interesting.
Thanks. Well, before we move on to questions from the audience, let me ask one more question, perhaps the hardest question of all, which is learning at the edge. How do we do it? Is it feasible? Does it make sense? What are your thoughts? Let's see, Song. Let's start with this one.
Yeah, I think learning on the edge has a lot of practical applications. It's definitely doable. Like the input method we use when we're texting. Those are using federated learning, and also the watches, if you're monitoring what is the activity going on, that's probably also an opportunity for edge learning. So there are two categories. One is just learning on individual device. Okay? The other is learning on multiple devices together. Right? On individual device, the challenge is that people previously talk about model compression, where we reduce the model size. But learning is different. We have to not only consider the model size, but also the activation is the bottleneck, since we have to store those intermediate activations for back propagation. So how do we reduce the activation size and selectively update the layers and channels to update and reduce the memory consumption, like Joe mentioned, which is the bottleneck for the power consumption of an edge device. So we propose a couple of techniques like TinyTL to update the bias only that can reduce the memory footprint. The second category is multiple devices. We want to jointly learn something together, right? So that's federated learning is a good example where each device don't send out their data, which is private. They only send out the gradient or the activations. So the gradient or the weights. So the challenge there is the communication. Okay, the bandwidth might be limited, the latency might be long. So how do we save the communication bandwidth by compressing the gradients, and also tolerate the delay, and also to tolerate the stale gradient during this kind of federated learning? Those are some of the challenges for on-device learning, but it's getting very promising. I think we are utilizing federated learning already in some of the mobile applications.
Rajesh, learning at the edge.
Sure. By the way, there's a question also. Is non-federated learning at the edge meaningful? Mm-hmm. So learning at the edge is actually important, and it's important for many reasons. Now, when people first started using deep learning, they said, okay, let's just send all the data to the cloud, and all the AI can be done over there. The edge device doesn't have to do anything. But reality is, as we are using it, our edge devices as sensors to the whole world, everything is being sensed. And at Qualcomm, we love communication link. We make it faster and faster. So we would love for everything to go to the cloud so that you can use our communication link and give us more money, hopefully. But reality is that it doesn't scale quite that way. So you do want to have learning at the edge also. One reason why you may, for example, want even a non-federated learning at the edge is personalization, right? I mean, I gave an example in one of the previous talks in a different location, is that I don't just want my phone to know that I like Indian food. I want it to know that I like masala dosa, okay, which is a specific thing, right? Now, this will require my edge device to collect some data about me, which it will. It does that all the time. And then now it could send that information to the cloud and do the AI over there, where it is much better that it does that locally, so that my information is not getting shared. And so in this particular case, the example that I gave you is not that important if the world knows about the fact that I like masala dosa. But in many other cases, you can imagine this could be very sensitive information. So that's the reason you do want learning at the edge. The challenge is there. One challenge that Song just talked about is that you do have to store the activations as you're going through the forward pass in order to do the reverse pass. So there are different things that you could do. First of all, maybe you don't have to learn the whole thing. You don't have to, do everything on the edge. You do some sort of transfer learning, or maybe some layers you do there. There is always this trade-off between, how much memory you need to use versus how much computing you can do to sort of exchange for memory, because putting more memory on the edge is going to be expensive. And of course, then you have to come up with the right way to do things. Joel, you mentioned that, okay, if you do something for one layer and then do the next layer, then you have to have a whole bunch of data that you have to store, send back and forth. Never want to do that layer at a time because it is expensive. So you have to come up with, smart ways to use that, and you have to do the same thing for learning also. So there are different techniques that can be used, but I do want to say that learning at the edge is important, and some of these techniques can be used to actually make that possible and more meaningful.
Varada, your thoughts?
Yeah, I love the masala dosa example. So yes, I think personalization is a very good reason why we would want to do non-federated learning learning at the edge. Again, I take the example of the robot that I started with, home robot. Every home is different. It's an unstructured environment. How do we adapt to an individual home? So the learning at the edge, again, if I really want to fulfill the privacy promise, I don't want to send all the data back to the cloud and learn at the cloud and come back, or update the model in different fashion. So I think learning at the edge will be critical. The challenge I see is, there are two challenges. One is, we are used to supervised learning. There was a nice presentation this morning on supervised learning or learning from noise. How do we get labeled data? Who's going to label the data? Yes, when you're typing, you can correct yourself, and that can provide a nice signal. So how do we get the right type of signal to label the data, to train the network becomes a challenge. And there are different options available. Each one of them is as expensive as running multiple networks, or maybe transfer learning in different fashion. I think each one of them have a challenge at least at this moment. I think there are good research going on this front that we'd want to definitely explore. And the second challenge is you definitely are working with a limited set of data. Yes, there are more sensors, there are more personalized data coming in, but there is less diverse data coming into your network. So how do you make sure that your training doesn't deviate from, your local training doesn't just take the full model and take it in a different direction that's not consistent with the larger model. I think those are the two challenges that I can think of. How do we learn with limited amount of data, and how do we label the data, or how do we go to a semi-supervised model or even unsupervised learning to learn at the edge?
Joel?
Okay, so I concur with, I think, everybody's initial point, which is that learning at the edge is very important. So I agree with that. And there's been a number of points made about how expensive that is. It's challenging because we don't have labeled data. It's challenging because that backward propagation and data movement is very expensive. Of course, the neural networks that we're talking about are brain-inspired, and the brain does have a structure that is kind of like the neural network that we emulate in the artificial neural network. However, the brain doesn't get supervised data. It also doesn't do back propagation. It doesn't actually separate learning from inference. It's all happening together. So my conjecture, which is maybe a longer-term research objective, is that we should continue to extend our emulation of the capabilities of the brain in our artificial intelligence. Okay, artificial intelligence systems. The way the brain, I'm not a brain expert. I do loosely collaborate with somebody who knows a lot more than I do. And the way the brain works, one is the entire network doesn't light up in response to every input. There is something that is controlling and selecting which pieces of the brain are actually active at any one time. And furthermore, when that piece is active, it is both simultaneously creating an inference and getting trained. And so the structure of the brain appears to be broken up into a part that looks like what we think of as artificial neural networks, and another part, which I'm going to label a controller, which has some short-term state that is continuously updated, and that controls which part of the brain is going to be doing something for the current function, and also whether it is focused a little bit more on inference or learning for this particular moment. So I believe in the learning at the edge. I think we have our work cut out for us in order to make it practical.
Definitely. All right, this is the moment to then move on to take questions from the audience. I don't know if it's all through the interface, or perhaps there's a mic for folks to ask a question in real time. Okay. All right, so the first question is up. I guess we're selecting those that have a number of votes. E-waste is a major problem for the environment. How can we avoid creating additional e-waste from new chips and devices while still fulfilling your visions for AI edge hardware? Who can take that?
Maybe you, Jesus.
I can take a stab at it. Look, people are not putting chips in everything necessarily just to do AI. Okay? They're putting it there to do sensing, which is actually necessary. You do want to have sensors to actually solve the problems that there are the other questions we're talking about that. So the question that we were trying to answer was, how do you add almost nothing to it, that what you had to just put in the sensor anyway, and then do the AI that needs to be done? So in some sense, almost all the things that we are talking about are going to not add any extra e-waste, use not very much power, actually reduce the power consumption for AI so that all of the other greenhouse emission and all of those things that we are talking about is reduced. So to me, it seems like that the vision that we are creating, that we are talking about, can actually improve the environmental problems that we are facing. Now, yes, it does require that you are putting sensors everywhere. Would you do better if you didn't put sensors everywhere? I'm not so sure. So in some sense, maybe there's some cost to be paid, the cost that you're paying, that you're putting sensors in everywhere. But then the benefit that you're getting is that you get the information. With the techniques that we are talking about, you're going to do the processing there with very little power, and hopefully that can solve other problems.
Mm-hmm. Anybody else wants to contribute? So?
Yeah, so there's a global shortage of silicon these days. So we think about this problem and try to simplify the algorithm so that even old chips, even old technology chips, we can run those neural networks on those old chips, right? For example, we can greatly simplify and compress and reduce the size of the neural nets, quantize them to 4 bits. So even the Cortex M7 microcontroller, which is definitely not 5 nanometer or 7 nanometer technology, those old chips can still do those real-time person recognition, right? And at Alamo ML, we are using a very old MIPS CPU to do the person detection and package detection to notify people, okay, there's a package in your home. Just using the very old MIPS CPU, very cheap, like $5. Those old chips without using like advanced specialized accelerators. So that might be a good way to improve the efficiency of computing by simplifying the algorithm.
Mm-hmm. Any other thoughts?
No, I actually agree with both Rajesh and Song. I think the focus is not AI for the sake of AI. What problem are we solving with the AI, and how do we solve it with the lowest energy is really the thrust of this conversation today. So yes, I agree with that. Yeah.
So there is a little bit of work, which is going to be further out. As Jesus answered before, new technologies often take a decade to reach fruition. There is a little bit of work today on biodegradable devices. So the idea is that the substrate is biodegradable, and that the other components, which are metal and some of those components, are extractable out of the chip. So essentially the idea is, can we make recyclable chips?
Yep. All right, let's move on to another question. I see there the question that has 2 votes. What is the next cutting edge application of neural networks and deep learning models that do not include applications shows for military or ageist models, e.g. making women appear younger. Okay, we need to parse this somehow. Anybody?
Yeah, maybe I can try. I think I'll talk about the robotic problems again, because I'm sorry to be just going back to the robots, because it's kind of my pet theme. Mobility. Mobility in detecting other agents in the environment. Mobility in detecting and navigating around obstacles in the environment. Those are neutral, essential applications that actually benefit everyone. It is, I don't know whether there is any specific bias that comes from where the application is. A good application that we are working for is how do we support, I think there was I think Dina Katabi or another presenter talked about in the morning, how do we detect, support aging population in disease detection, or in I think gait detection, and support the elderly at home, and enable other uses of robots in the home. I suppose those are applications that are novel. I think they are useful for all the population. That's my take on that question.
Actually, I think the next question, the one that has 3 votes, also is related to this one, and it focuses again on human problems. How can we apply AI with co-design with hardware to tackle some of our biggest human risks, like identifying polluted water and air? Also, can we create AI hardware with non-hazardous materials?
I think we are talking about, AI is already being used by a lot of applications, okay? And not everything is as frivolous as we talked about before. We give those examples because they attract attention. Mm-hmm. But image processing, for example, just to make sure that your pictures look good, okay? You may think that it's no big deal, but turns out that using AI for that is very useful. A simple example being that you take a photo, there is sky, your face is there, and forget about trying to make you look younger, although I think that's a noble cause, by the way, for us, all of us to look good. But think about your hair. Hair has more texture, high bandwidth content, so to speak. Face, you want it to be low bandwidth content because it's a little smoother. So this happens already in your phones. Different example. I want my chips to be smaller. Qualcomm makes chips. I want my chips to be smaller. Using AI, the design time is faster. The chips that you design with AI are smaller. Is that a good thing? Well, hopefully, if you use slightly less silicon, the amount of waste is ultimately smaller. Here we are talking about water pollution and air pollution. We are talking about sensors everywhere. They are there to do exactly those kinds of things, to find out when a particular pollutant is entering water or air, and try to take corrective action earlier. So really, if you can't monitor what's happening in the environment, you can't do something about it. Almost everything that we are talking about allows us to monitor our world and hence do something about it. Even simple things like making sure that you know where the traffic jam is and avoid that, and use AI algorithms to make that happen, reduces greenhouse emission because people are not idling in their cars. So almost everything that we are doing, one could do frivolous things with them, but one could do some really good things with them. So I think that what we are doing is a noble cause.
Mm-hmm. Any comments, anybody else?
I guess I wanted to tease apart a little bit of the implication in the question in terms of co-design with hardware. Hardware takes longer to design and manufacture than writing new software. So in some ways, and you alluded to it before, which is the objective of hardware designers, I believe, should be to design the most general capability possible while not sacrificing very much efficiency. And so sort of deciding where that trade-off is one of the biggest challenges. Once you know something is important, you can specialize. But in order to do a new application, like detecting air and water pollution, we're going to use existing hardware. We don't have time to spend the 2, 3 years or 4 years that it takes to actually create new hardware from scratch. You might modify something that exists, but not designed from scratch. And so, that application, I imagine, is going to happen with existing hardware targeted at a new application domain. And like I say, it's incumbent upon hardware designers to come up with hardware that is broad enough in scope to be able to take on these new applications.
All right. Next question. I like the one that's there, the U.S. National Security Commission. The U.S. National Security Commission on AI highlighted that leadership in AI would need a robust and secure chip industry. Is that going to happen? Maybe I'd like to say a few things about this. So as you know, there has been a huge effort in the United States now for the last 2 years or so to think through what would it take for the U.S. to regain leadership in semiconductor manufacturing. It's a long debate going on. The legislation has been proposed. It hasn't quite passed completely yet, so the programs haven't been launched. But it's pretty clear that something big is going to happen. However, the thinking that has gone into answering this question, which is, is it feasible to have a fully robust and secure chip industry in the US, has been very valuable. And in fact, the conclusion is no, there is just not enough money in the United States to have a totally robust and secure chip industry. It's impossible. The industry is just way too large. So what we have to do is be very strategic, focus on really key strategic areas, particularly focus on the future and focus on innovation, and also build very strong alliances with like countries around the world to build very secure supply chains that will make our access to chips completely secure, the most advanced chips. So this is a wonderful discussion that's happening right now. I think there's going to be a lot of activity in the United States in the next few years, and we hope us in universities to play a role in this. All right, we still have time for maybe one more question. Going back to AI, can we deploy the deep learning model or reinforcement learning agent in the existing limited computing power hardware, e.g. 10 years old CPU chip with a tiny ML optimization? I think someone has been talking about this.
Yeah, we've shown some demos, like Cortex M7 microcontroller, which is pretty old technology. But the key idea is to co-design the neural net with the inference engine. And we have to turn a lot of runtime stuff into compile time, and also do extreme co-optimization both of the runtime and also the neural net. For example, you want to fit the weight, the activations with the cache, the size of the cache on those super old chip, which has very small amount of parallelism and a small amount of cache, where the constraints are tighter, but neural network architecture search can help with those scenarios.
Any other comments? Let's see, maybe we can bring another question. We already talked about e-waste, right? How about, is non-federated learning at the edge meaningful? Who can handle that?
Rajesh already answered that.
I think we already talked about that. Yeah, personalization is a very simple example, but there are others too. Yeah.
It is. More questions? All right, then we'll take this one about e-waste. If we can bring it up again, we still have 1 more minute. No?
That was the response to the e-waste question.
Yep.
Reducing cloud inferencing is a major benefit to environment in terms of substantially lower energy consumption. I would argue this is a net positive by a large margin.
Yeah. So
nailed it. Any more questions? We have 1 more minute. All right, if not, I want to thank the panel for a very engaging discussion. Thank you very much.
Thank you.
Thank you.